will be shared. So take this one and share. And then my lecture will be shared on Zoom as well. Okay, so if you want to, unfortunately, I did not turn on Zoom early in the class. So some of the introductory materials will not be in Zoom, but starting from this point, I think it will be in Zoom. Okay, so why study electromagnetic field theory? Well, there are many good reasons for it. It is one of the most important theories in electrical engineering. It's been around for over 150 years. And you will read the lecture notes. The thing that drove the onset of electromagnetic theory was technology. And at the time, it was the call for telegraphy. How do we send signals along telegraphy lines? And that caused many of the theories to be formulated at that time. So electromagnetic field theory is essentially just Maxwell's equations. And this theory, amazing thing about it is that it's valid from atomic length scale to galactic length scale. That means that if you have somebody going to Mars, or maybe sending something that probes the outer spaces, we can communicate using electromagnetic waves. The fact that we are listening to radio waves from other systems light years away is because electromagnetic theory also works across galaxies and so on. Okay, so the second thing is that electromagnetic theory is relativistically invariant. That means it doesn't matter which inertial frame you're in. But if you have not studied relativity, that's not important. Okay. The third thing is that electromagnetic theory is valid in the quantum regime. Quantum regime is becoming very, very important these days because of things like quantum computers, quantum communications, and so on. So if you know how to do some calculations using classical Maxwell's equations, you are quite well prepared to do calculations in the quantum regime as well. Okay, and then electromagnetic theory is in harmony with differential geometry, which is quite a recent branch of mathematics that came about in the 1940s by this Frenchman, Eli Cartan. Okay, you can formulate electromagnetic theory using differential geometry. Otherwise, we just go to some very old calculus that we learned from Newton, Leibniz, and those people like Stokes and Gauss and those on. Those people lived in the 1800s, 1600s, 1700s, and 1800s. They formulate a kind of mathematics which is differential calculus. But the more modern form of calculus is actually differential geometry. And the electromagnetic theory is one of the most accurate equations that we have ever formulated. It's valid to a few parts in a trillion. And because of the omnipresent and the high accuracy and pervasive use of Maxwell's equations, this theory is very important in electrical engineering. For instance, in the low frequency regime, if you work with circuit theory, if you work for a computer chip company, where the signals are on the order of maybe megahertz, kilohertz, and gigahertz. And do you know how long the wavelength is if you have a 1 gigahertz electromagnetic signal? Does anybody know? Nobody knows?
Is it like 1,000?
1,000 nanometer?
It's like a micron.
A micron? I think it's still too small. The way I remember it, when I was an undergraduate, I used to work in a microwave lab. The thing I keep in my mind is 10 gigahertz to 3 centimeters. Okay, because why microwave? Microwave engineering is very prevalent because you work with components of the order of wavelength. and the microwave wavelength is about 3 centimeters. So you just scale everything. So 10 gigahertz is 3 centimeters, 1 gigahertz is 30 centimeters. You can also think that in 1 nanosecond, electromagnetic wave travel a distance of 30 centimeters. You work on the math, okay? So it's important in microwave. It is important in circuit theory, where of course the frequency is much lower. Like if you work with the AM920 station that we have, the wavelength is on the order of a few hundred meters. But electromagnetic theory still works for that radio station. And if you go and work for a professor in the field of optics, then you will have to go to very high frequencies. Like blue light is about 500 nanometers. If you work with ultraviolet light, it's about 100 and 200 nanometers. UV lights are now used for lithography because we need to make computer chips that are very, very small. The only way to make them is to use ultraviolet lights. So those are electromagnetic radiations as well. Okay, and you do that with bioelectromagnetics as well. Okay, there are all kinds of things you can work with, and electromagnetic field. And this is something that I put up maybe 20 plus years ago. I only had the blue items, okay? But then I find that some 20 years later, this chart still remains very important, electromagnetic, all these different areas. I guess those are brown colors, right? It affects small antennas. If you go at the bottom, why small antennas? Because everybody carries a cell phone now. Your cell phone cannot have a big antenna. So it has to have very tiny antennas that fit in. And many engineers go about designing those antennas. Then there's this field of EMC, EMI, which stands for electromagnetic compatibility and electromagnetic interference. And then stochastic modeling, because things are so random in the world now. You have to put in some randomness, and those are done with stochastic modeling. And now you have the field of nano optics, nano antennas, and metamaterials. Okay, metamaterials are just man-made materials. They're not materials that come from nature. Okay, why nano optics? Well, the reason why nano optics is becoming very important is because of nano fabrication. We can make things that are really small now. In the past, we can make mirrors, we can make lenses. But now we can etch things that are much smaller than the wavelength. I told you a moment ago that blue light is about 450 to 500 nanometers. But we can make things even smaller than that. Do you know how small a transistor is now? Does anybody know?
7 nanometers.
About that 5 nanometers. I think Samsung claims that it can make 5 nanometer transistors. Okay, you can see that transistors themselves are very much smaller than the wavelength of light. Okay, so because we can make such small things, you can make optical devices that are very, very small now. Not like big lenses. In the past, we used mirrors and lenses to do optics, but not anymore. We do a lot more complicated things. And then if you go to the quantum world, you can do quantum optics, Cosmic force, heat transfer, quantum information, plus many more. I wouldn't go through this chart. You can read this chart, and if you have any questions, you can ask us. Okay. And this is just a brief history of electromagnetics and optics. You probably have read or learned from your undergraduate courses that in the beginning, people thought that electricity and magnetism, which is on the left-hand side, the left-hand column, is different from optics, which is the right-hand column. That was in ancient times. Okay, of course, on this side, there are things like lodestone compasses, static electricity, and then came telegraphy. when telegraphy technology came about, Ampere's law, Faraday's law, Kirchhoff voltage law, Kirchhoff current law, and all those became very important. Okay, and that was called electricity and magnetism. And then on this side, you have what we call optics. Optics actually, the Chinese knew about pinhole camera, module, know about pinhole camera. The Islamic world, Ibn Sa'd, knew about Snell's law and the kind of thing quite early. Snell's law in the 1600s. And then you have a whole branch of knowledge that's been developed. It was not until 1865 when James Clerk Maxwell published his theory. And his theory shows that light and electricity and magnetism can be described by one set of equations called Maxwell's equations. Okay, so because of that, then everybody jumped on the bandwagon and started to study these equations mathematically. And then you have quantum electrodynamics and so on. Out comes the electromagnetic technology. Things like radar and wireless communication, and then you have nanofabrication, single photon measurements, quantum optics. And I believe that this is going to be a very important area in the future, which is quantum electromagnetics. Okay, so this is actually what I'm going to cover today. Let me see, I still have some time left. Okay. So first, I'd like to talk about Maxwell's equations in integral form. I usually prefer to write out the lecture notes so that you can follow and you can follow at a more leisurely pace. Okay, so let's talk about Maxwell's equations in integral form, and that was what things were in the beginning. And let's talk about Faraday's law. I presume you have had this before coming to this course. And if I were to write Faraday's law, this is the way I write electric field. This is the line integral. And if I were to write this thing, Faraday's law says that this is proportional to the flux linkage. Okay, the flux linkage B dot ds. Okay, this is Faraday's law. I hope you all understand this notation. Otherwise, you will have to go and read my ECE 350X lecture notes, or read a undergraduate EM course before you join this course. Okay. So this law essentially says the fact that if I have a loop, if I were to integrate the electric field around the loop, say if I have an E field, okay, and if I were to integrate it around the loop, a metal wire, for instance, and if I have a B field, it goes through this loop, it goes through this loop in different places. You perform this surface integral, which is taking this B field and dot with the small area and integrate over this cross-sectional area. That's called the flux linkage. And the rate of change of this flux linkage is equal to this integral, which is the voltage. Okay, this integral will give rise to a voltage on the left-hand side. I hope you're familiar with this from some undergraduate courses. And of course, you can think this and convert this into a solenoid. Okay, instead of using a single turn, you can multiply turns. You link with a B field that goes through many turns. And this is called a solenoid. Okay, any questions on Faraday's law? It is a pretty important law. The amazing thing was that it was discovered experimentally. And then we have Ampere's law. And this law is very similar in appearance to Faraday's law, except that on the left-hand side, you will have the magnetic field integrating around a contouring state. And that integral on the left-hand side is equal to the integration of the current. Instead of the B flux, you integrate the current flow over a surface S. And then you have a term that looks like the right-hand side of Faraday's law, but something that says that this is equal to, oh, sorry, there's no closed loop around the thing. Okay, this term looks like that term, but there's a difference. There's a plus sign here, there's a minus sign here. This is D instead of B. This is electric flux linkage. The other one was magnetic flux linkage. Ampere's law says that the integral on the left-hand side, which is to calculate the effective of the magnetic field going around the loop, is equal to the total current that flows through the loop plus the time rate of change of that flux linkage. So you will also have a loop C, like here we had a C before, and then you look for the J that goes through that loop C, and then look for the flux linkage D that goes through the loop. Okay, that is Ampere's law. Ampere initially wrote this law without this term. He just wrote it with the first term, experimentally determined, found that the first term is very important. It was Maxwell who came by, who added the second term. The second term is called the displacement current term. So it's the second term that changed the world. Okay, without the second term, we would not have electromagnetic wave propagation. It is the presence of displacement current that allows energy and wave to go through vacuum and free space. You probably have heard about displacement current in the capacitor. So displacement currents can go through insulators, as is the case of a capacitor. Okay, any questions on that? If not, let's move on and talk about Coulomb's law. Coulomb's law, what is it? It's just a statement that if we have electric flux, and if you integrate over a closed volume, closed surface S, it should be equal to the total Q charge inside. So if I have the surface S, and then if I have some charge Q inside, and this Q will produce electric flux B, exuding from these charges. And if you were to integrate that B over this surface S, you find that that integral gives you the total charge enclosed by the surface S. That is Coulomb's law. Okay. And then the last law that we should have is Gauss's law. Gauss's law is very similar to Coulomb's law, and some people also call this a Gauss-Coulomb. Gauss' law is very similar, except that you work with magnetic flux instead. And if you work with magnetic flux, take any surface S and look at the B field that goes through that surface. And if you were to perform this integral, it always goes to zero. It always goes to zero because there's no magnetic charges in this world. Okay, that's Gauss's law. So, any questions so far? If not, let's revisit this law in the case of statics, okay, which is what I'm going to talk about next. What happens if there's no time variation, partial t of d dt always goes to zero? And if you look at the previous two equations that we have written down, if d dt go to 0, this term drops out. This term will have dropped out. This term will become 0 if d dt equal to 0, and in Faraday's law, the right-hand side will drop out. So for static electricity, okay, where d dt is equal to 0, you will have the fact that Faraday's law just becomes this, because the right-hand side is equal to 0. And Ampere's law will just have one term on the right-hand side. It only involves the current integration. Okay, and then this is the total current I. And then you have Gauss's law for magnetic flux, which remains the same, because there's no time derivative in that equation. And then you have Coulomb's law or Gauss's law for electric flux. It will just be equal to Q. Okay, so this is just static electricity. Static electricity is a lot simpler. If you look at Maxwell's equations, they're even simpler than those compared to the dynamic ones. Some terms are missing. Because of that, the solutions can be found very easily. So let's look at Coulomb's law. Coulomb's law, the way it was stated originally was quite different from what I said just now. Okay, Coulomb's law is actually formulated around 1785. Okay, what it says is that if you have two charges, and these two charges have different magnitude, Q1 and Q2. And if these two charges are of the same polarity, if both of them are positive, then there will be a repulsive force between them. However, if one of them is positive and the other one is negative, there will be an attractive force between them. And the force is always in the direction of the vector that points from one charge to the other one. And I can denote this vector as R. And then I can use R12 hat to denote this unit vector. We will use a hat to denote a unit vector. Okay, everybody knows what a unit vector is. Okay, it's a vector with unit magnitude of 1. And Coulomb's law essentially says that the force between these two charges, which is a vector, I use a bar to denote that this is the vector. It is proportional to Q1 and Q2, 4 pi epsilon R squared. And then this force is in the direction of the unit vector that points between the two forces. This law is also determined experimentally and empirically. Okay, you can write this thing in the fancier fashion. You can write R12 hat as being equal to R2 minus R1 over R2 minus R1. Can everybody see that this is in fact a unit vector? You take the difference of two position vectors. These R's are called position vectors. And if you don't know what they are, you can go back and revise your vector algebra. And take this vector and divide by its own magnitude, then this vector would be of unit 1. Okay, it has always a length of 1. And this is called a unit vector. And then you can write Coulomb's law in terms of these unit vectors if you want to. Okay. So let's talk about something else then. If you don't have question on Coulomb's law, which is something that we have learned as an undergraduate, yes?
So the Coulomb's law that you're describing there is different from the one in Maxwell.
Yeah, that was actually called Gauss law, Gauss-Coulomb law.
Right.
It has an integral. But this was actually what was discovered by Coulomb initially. And you can show that the other law can be derived from this simpler law.
Well, you'd also need like the Lorentz force, right? Because
There's no force here because there is something called Lorentz force law, which is correct. But Lorentz force law is not involved here. You can say that this force that we have here is part of the Lorentz force law. Because Lorentz force law says that the force is actually equal to QE plus QB cross B. You have to have a magnetic field involved, electric field involved. Okay, we are actually just working with the first part of Lorentz force law. Okay, so very good. It has something to do with Lorentz force law. And let's elaborate on this further. So we assume that there's no magnetic field, but just electric field. And that if we have two charges, Q1, Q2, let's say Q2 is a small charge, incremental charge. And then the unit vector between them is r hat, and then the distance between them is r. And then I can write the force as being equal to r hat q delta q over 4 pi r squared. R here just means that, okay? When you take a vector, a position vector takes a magnitude, it becomes a scalar number. And then I just denote by R. And the numerator is actually Q1 and Q2. Okay, this is just Q1, Q2. Okay. Then you can derive what is called an electric field. Electric field being equal to the E times delta Q. In other words, the force is proportional to the electric field times the charge, which is just exactly what Lorentz force law is if you just have the first term. And using this concept, you can arrive at the concept of an electric field, which is taking the force between two charges and then divided by the charge density. And you'll find that electric field due to a point charge, you can go through the math quite easily. If you write in a coordinate independent fashion, this would be just equal to that. And I just write it as this. And actually, if we were to write this out more elaborately, it would be Q R1 minus R2 over 4 pi R1 minus R2. Okay, square. So this is the definition of the electric field. You can think of if you have a charge Q here, and then if the distance between these 2 points are R and R prime, and then there would be an electric field going from Q to this point R prime, given by this formula over here. Okay. Any questions so far on this? Yes.
Did you drop the epsilon value in the equations?
Yeah, I think I did. Yes. Yes, I did. There is an epsilon somewhere. There is an epsilon somewhere here. Yeah, I have an epsilon above there. So the epsilon should carry over. Very good. Thank you for pointing this out. So there should be an epsilon here. There's an epsilon here. And so on. Okay, thank you for pointing that out. You can go on and think of having linear superposition of point charges. Okay, and then the electric field due to a linear superposition of point charges is the linear superposition of the electric field due to each one of them. This is called the principle of linear superposition. which is used a lot by electrical engineers. It only works for linear systems, and the electrical engineers love linear systems. Okay. So if you use the principle of linear superposition, you will have the electric field due to these point charges as being due to that. Any of you is a mechanical engineer here? No? Okay. Because in mechanical engineering, linearity does not apply very often. So you have to deal with nonlinear systems. And analyzing nonlinear systems is a lot more difficult. Okay, so if we further assume that Qi is rho I, which is a charge density times the small volume at that location, this is charge density. Then you can rewrite this as being equal to I equal to 1 to n rho Ri delta Vi R minus Ri over 4 pi epsilon R minus Ri. And this will be something that will come out useful, come to be useful later on, because this is essentially the precursor to an integration. This delta V can become a dV in an integration, and then you have the charge density, and then I think there should be a square here, sorry. 4 pi epsilon R minus R prime squared. Okay. So you will come across this kind of expressions in the future. That is, if you have a cluster of charges or charge density, the electric field due to that cluster of charges is given by that expression over there. Okay. So, any questions so far? Maybe I'm going a little bit fast.
I just have one question.
Yes.
Does the sum apply to the whole thing or just the numerator?
The sum applies to whenever you have a subscript I. So let's see where subscript I is involved. Okay, subscript I denotes the location of that point charge. If you look at the first expression, that I refers to the location of that point charge that you're referring to. Okay, and there were many of them, there were n point charges, so I goes from 1 to n. Again, I can denote the Q sub I, it should be I. I didn't write it too carefully. And rewrite the sum in this fashion. And if I write the sum in this fashion, it looks strikingly like an integration. Okay, then I can replace it with this thing. And I replace the R sub I with prime because now it becomes an integration variable. And I have the last expression. Okay. Yeah, this, you will later learn that this is called a green function. You don't have to worry about green function right now, but that is what it is at this point. So let's go on to derivation of Gauss's law from Coulomb's law. Okay, and somebody mentioned that the Coulomb's law that I talked about just now was different from the Gauss's law that I had earlier. It turns out that you can actually derive the other law from Coulomb's law. That is, that if I have this law, which I call Gauss's law, over a closed surface that equals Q. Okay. So I'm not going to go into the detail about this, but essentially what it says is that if I have a point charge, it gives rise to electric field that looks like this. The D, or the electric field, D and epsilon E are related to each other. So if the flux looks something like this, which is we showed earlier on. The electric field looks something like this. Okay, D and E are related. So if you have a point charge, it gives rise to electric flux like that. Okay, so if I take this thing and everything is spherically symmetric, as you can see, if I were to integrate this over a closed surface S, okay, it will be just equal to the flux density on each surface times the area of the sphere surface. And that should be equal to the charge inside. Okay, can you see that? So in the sense, if I look at Coulomb's law this way, if the electric flux are due to Coulomb's law, the way I've described in the previous slide, if I were to integrate those flux over a spherical surface, it should be equal to the charge Q inside, which is what this other version of Coulomb's law is. Okay, but let me be imaginative and argue that this is irrespective of the shape of the surface S that I'm integrating over. Let me distort this surface S a little bit. Okay, take another surface S that looks different from the original surface, which was very nice. It was a spherical surface. Everything was symmetric. You can do the integration very easily. But I'm going to argue that if you take a different surface S that looks different from the original one, you're going to get the same charge Q. I set out the argument more carefully in the lecture notes to argue that irrespective of the shape of these two surfaces, you always get Q inside. Then from this way of argument, you can see that Coulomb's law actually gives rise to Gauss' law in the top line. Okay, because it doesn't matter what shape you are. So if I have a point charge here, it doesn't matter if I were to pick a surface S that's very different from a sphere, and I'm going to pick out this charge Q if I integrate the flux over the entire surface. So if I have a cluster of charges here, you always give rise to the charges that is inside the surface S. Okay. So any questions before we move on? If not, then let's move on to Maxwell's equations in a differential operator form. We have written Maxwell's equations in terms of integrals. And it turns out that in most of the courses and most of the textbooks and most of the physics books that you see Maxwell's equations, they're not in the integral form. They're in a differential form. I would say differential operator form because the use of the term differential form can be quite misleading because it implies something different in mathematics. Okay, so let me just write down Maxwell's equations in integral form. And that we have done before. And these were originally written by the experimentalists. Okay, this is Faraday's law. And then this is Ampere's law. Plus the total current I. And then we have Gauss' law, okay? Sometimes called Coulomb's law as well. I would call it Gauss-Coulomb because the two are very similar. And then I would have truly Gauss' law, okay? I'm going to derive the differential operator form, not differential form. Because differential form refers to something in differential geometry. And I do not want to confuse the two. Okay. And many of these mathematics were derived by Gauss, and Gauss is a genius because Gauss lived from the 1700s. To 1800 plus. Okay. And here I will derive for you what the divergence operator is. This is called the divergence operator. And then I will derive for you what the co-operator is. Okay, sometimes this is called a rotation operator. Okay. So the divergence operator is defined in the lecture note. Divergence of a flux B is defined to be, take a very small volume, perform this operation, that is, integrate the flux. Say if I have a flux B that goes to this volume, I take this flux and integrate over all the 6 faces of this cube. Okay, and let me call this surface delta F. Okay, there are 6 of them. You perform this integration, count all the fluxes properly. And then after you have counted the fluxes properly, and if you make this volume very, very small, what happened to this integral on the right-hand side? Yes? I count this flux through that small volume. And if I make that volume very, very small, what happens to the right-hand side? Becomes small, very good. It becomes small, it will eventually go to 0, right? So that's no good. So I normalize it by the volume of this small cube over which I'm doing the experiment. So if I do it this way, you'll find that this ratio becomes a constant. No matter how small you make the cube is, this ratio is a constant, which means that you can define the divergence of B with respect to a point in space. Take that point in space, draw a small cube around that, and perform this integration. Okay, but also normalized by the small volume. Find that it becomes a constant. The algebra is done in the lecture notes. I wouldn't go through the algebra here because it will be too boring for you. It's beyond you anyhow, because you probably know how to do that if you have the patience. Okay, so you find that this divergence of B, if you do all the algebra correctly, is given by this expression. If we assume that the vector D has 3 components, and this is the notation that we will use in this course. Okay, vector D in the Cartesian coordinate is denoted this way. The x hat, y hat, and z hat are unit vectors in the Cartesian coordinate system. Whereas some textbooks may write it this way: dx, dy, dz. That is okay. Doesn't matter how you write it. It means the same thing. Or some textbook might even write it with I, j, k. Okay, but no matter what you see, they mean the same thing. You just have to know how to translate from one form to the other form when you see them. Okay, but I'm not going to derive this identity. You read it up in the lecture notes. Okay. And the lecture note will go through that. Okay. And you can go through all the counting, and then you will have something very interesting. But what is important is that using this identity, that divergence of B is defined to be that. Okay, divergence of B is defined to be that. You can perform a small thought experiment or Gedanken experiment, as the German calls it. Okay, so you can assume that you apply that small definition of divergence of B to each of these cubes that you have inside the volume B. Okay, let's apply that to each of these cubes that we have seen here. Apply that small identity that I have written down in the previous slide. And then I take the divergence of B and integrate over the volume, the entire volume B that contains all these little cubes. Okay, but each of these cubes can be replaced with a surface integral. That means that I can divide this into okay, I can break the cube up into tiny, tiny little cubes and then perform these experiments for each of them, and then make use of the definition of what the divergence of B is. Divergence of B is just integration of this very little cube, small cube over the SI over delta VI. Can you see this? I break the integration over the entire volume into small pieces, and then look at each of the tiny pieces that I have, and that can be replaced with this identity from the definition of what the divergence is. And I have the divergence definition in a few slides ahead of us. Okay, this is what the divergence is. I'm saying that I'm not going to prove it. It's proof in the lecture notes. So if I go back to this, I will have this. And now if you take this small surface integration that I'm performing for each of the terms on each of these cubes, count the fluxes that are flowing out of them. And you see that those fluxes are canceling each other, except for those that are on the boundary. Let me see a picture that shows that. Yeah, what I have a picture that shows it as well, which is this picture over here. So if you look at each of the cubes, the integration that shares a common surface cancel each other. Can you see that? Only the integration remaining on the outermost surface do not have somebody to cancel with. Okay, so if you were to perform this experiment to all the cubes that you have here, all the inner surfaces will have the flux cancel with each other, leaving only the fluxes on the boundary. Okay, so what you eventually have is that that this integration would finally become just a surface integration on the outermost surface. Okay, it only involves integration on the outermost surface in this Gauss divergence theorem. Okay, this is called it Gauss's divergence theorem. I did not argue very rigorously, but you can see the idea here. Okay, you can see the idea here that integration of a volume divergence becomes a surface integration. So what we eventually have is that if I have a divergence of something, and I integrate over a volume V, it is going to be only the integration of the flux on the surface of that thing. This is called Gauss divergence theorem. So if I take Gauss Coulomb law, okay, if I take Gauss Coulomb law, which says that D dot ds is equal to Q. Okay, this is Gauss Coulomb law. And then the right hand side, I can also write it. Sorry. Yeah, I can write the right hand side as a volume integral as well. Okay, I can write the total Q as a volume of the charge density over that volume V. And then I know that this is true. I know that the V divergence of D of R over V must be equal to the V rho of R. Okay, what I'm doing here is to use Gauss divergence theorem to rewrite the left-hand side. Can you see that? The Gauss divergence theorem says that the left-hand side is the surface integral, but it should be equal to the volume integration if I replace D with divergence of D. Sorry, there should be a dV here. Okay, so I have converted Gauss Coulomb law into the last line here. Can you follow the logic here? Very good. So now I can make that volume very, very small. I can make the volume very, very small. And so it just involves one point in space. And this relationship can be written as this divergence of D for that point in space equal to rho of R. Can you see that? So I have converted an integral form of Gauss Coulomb law, which is the second line, into a differential form or differential operator form. To most mathematicians, the last line is more elegant because it does not involve integration anymore. It involves derivative and partial derivatives. I can derive partial differential equations from this equation. Okay, so there's one thing that we have successfully done here. You can do the same to the other equations of Maxwell. And before we move on, when we have divergence of D equal to 0, okay, it just implies that the integration of the flux through a closed surface equal to 0. And that would also apply to divergence of B equal to 0. This would imply that, okay, this is, say, if there's no charge inside the surface S, this integration is always equal to 0. And how would you say this in a very glib fashion? What goes in must come out, right? Can you see the physics here? What goes in must come out. That's what this law is saying. This is what Gauss divergence law is saying. Okay. So we can do the same thing to the other equations that we have. we can do the same thing to Stokes' law. And maybe before I do that, can I ask if you have any questions? No questions. So why don't we just regurgitate what we have learned so far? Because I might have been going a little bit fast. Okay. So we started out by going through this history of electromagnetic field theory, all the wonderful things that you can see. I would like to say that from electromagnetic field theory, you can derive circuit theory, but not everything in electrical engineering. A large part of electrical engineering follows from electromagnetic field theory. So circuit theory can be thought of as being derivable from electromagnetic field theory, except for the transistors and the diodes part. In order to derive those parts of circuit theory, you have to go through other physical theories. Okay, otherwise, a large part of electrical engineering is electromagnetic field theory. And if you work with wireless communications, you have to deal with electromagnetic waves. So there are lots of things that you need to use in electrical engineering that's related to electromagnetic field theory. And I went through this picture, and then I went through a brief overview of the history. Essentially, what it says is that in the beginning, people thought optics and electromagnetic fields are different things, but actually they are the same thing. The most important thing that brings this together is the fact that in this side of the world, people know how to measure mu naught and epsilon naught. Okay, and then when they put Maxwell's equations together, they find that the velocity of the wave that corresponds to Maxwell's equations is given by this, and they find this to be a tremendous, huge number. And they found that this number is close to the velocity of light. Because on this side of the community, they were also studying astronomy. And they were using the eclipse of the stars and that kind of thing to figure out how long it takes for light to travel through the universe. So they more or less knew about the speed of light. And then that brings these two things together. One of the very interesting things is that people figure out how to make electrical machinery in 1832, even before Maxwell's equations were completed. Okay, now Maxwell's equations lead to a whole bunch of new technologies that are very interesting. Okay, so we revised Faraday's law, which you have learned before, and then we revised Coulomb's law, all in integral forms. And then we look at the static form of these laws, which are something like this. And then we look at Coulomb's law in this early form. It's just a statement about the forces between 2-point charges. And you can actually see that this law is actually part of the Lorentz force law. Okay. And from this law, you can define what electric field is. And you can define electric field to be such. You find the electric field is given by this expression over here. Okay, and then we go about trying to ascribe Coulomb's law as to be coming from Coulomb's original law. We argue this true, but it's derived in greater detail in the lecture notes. And then we say these are Maxwell's equations in integral form. So we like to derive Maxwell's equation in differential operator form. So we started to derive what the divergence is. And then you can go through the same exercise, derive what the curl operator is. It's done in the lecture notes. but you go to the same thing, you find that curl is defined to be something else. And so maybe I have a few more minutes left. I can talk about the curl operator. So we know the divergence operator. Do you have any questions before? Yes.
Sure. So for most of these equations that we talked about, should we know how to derive them, or are we mainly going to be concerned with using them and applying?
I won't hold you responsible for deriving all these operators, but you should at least know their physical meaning.
Okay.
What the divergence operator is.
And same thing with Maxwell's equations. We don't need to worry about deriving them, just application.
Yeah, you should, after this, you should at least memorize those equations.
For sure.
Okay. After memorizing each of those equations, try to understand what their physical meanings are. Okay. It's very important to understand the physics behind the mathematics. Okay. So if I were to say, look at these equations. What is the meaning of this equation? This equation essentially says that the left-hand side is a computation of voltage around a current loop. Okay, that voltage, if I compute according to the left-hand side, will give me a voltage on this current loop, and that is proportional to the flux linkage B or dB dt. The time variation of the flux linkage through that loop gives me the voltage. Okay, that is essentially Faraday's law. And then Ampere's law essentially says that if I have a current I, this current I will produce a magnetic field H. And if I ignore this term for the time being, that magnetic field is given by this Ampere's law. And you can actually apply Ampere's law and show that, well, if I were to integrate this H field, H phi, let's assume that this is H phi 2 pi rho. Okay, let's assume that this circle is of radius rho. And if I integrate this H field about that circle, I get H phi 2 pi rho. That should be equal to I. And that immediately gives me an H phi that is equal to that. Okay, so I can apply Ampere's law and get what the magnetic field should be when I have a current. But Ampere originally ignored that displacement current. That displacement current is not important if you're in static, if you're in a low frequency regime. So things are very, very, very slowly with respect to time. So that second term was ignored by Ampere, and during his time, people do not work with high frequency. They work with telegraphic. Telegraphers work with tick-tock, tick-tock, they're very low frequencies, right? So they didn't know that that term was important. Yes?
What happens when U is 0 and variable? Because I remember you had a constraint on it in one of the first slides.
What is that?
I think you had a constraint in one of the first slides that like E can be 0, or the time derivative of E can be 0.
The time derivative of B can be 0 when you're talking about statics. I think I later on assumed that I have electrostatics. Did I go to static finally? Let me see. Yeah, I go to statics. And if I go to statics, d dt is 0. Then I can drop many terms in Maxwell's equation. So I will have this Faraday's law, which actually becomes Kirchhoff's voltage law. Because if you were to integrate this around any loops that are closed, It says V1 plus V2 plus V3 plus Vn must be sum of Vi, I equal to 1 to n must be 0. This is Kirchhoff voltage law. Okay. And then the second one is, of course, Ampere's law, the way he found it originally experimentally. And he ignored the time variation of the field. Okay. So he ignored completely the time varying term, which is this term over here. Okay. Well, during his time, maybe that wasn't too important, but it is very important in our modern world. Because without that term, we cannot have waves. And you are all good electrical engineers. So without that term, you know that you cannot have currents flowing through a capacitor. Say if I have a capacitor, you know that all good electrical engineers know that if this is voltage V, am I right? So when the frequency goes to 0, the current I so when the frequency is 0, there's no current flow. Is what we learn as good electrical engineers. But we know that if omega is not equal to 0, there's a small amount of current. That current we call the displacement current that flows through the capacitor. And that current flows because we have positive charges on one side of the capacitor plate. And if you reverse the sign of the current, the positive charges are going to discharge, and then they're going to move over to the other side of the plate. And then you will have like the electric field was like this originally. And then after you go through the next cycle, the electric field becomes like this. The electric field is flipping back and forth. And as it's flipping back and forth, there is a non-zero current in the wire part. And that current is due to displacement current. And I guess at that time, I don't know why Ampere ignored it. He just throw it out of his equation. Okay, and then if you don't have that term, you don't have waves. Something very important. Okay. Okay, I guess I wouldn't derive Stokes' theorem here. I'll derive it in the next lecture. But any questions so far? No, then go back and read your lecture notes. Okay, I can also give you an updated version today so they can read the lecture notes with the updates. Because I found a number of typos there, and I see you on Thursday then.
We've got a provincial. Yeah, I'll take that on. All right. I'll walk part of the way. Thank you.
Okay, thank you for coming.
I was curious, yesterday, like a little introduce yourself form, is that just a suggestion of right?
Oh, that was the point that I'd like you to introduce you to him.
Okay.
Yeah, so you fill it out so I can know who you are.
what area you came from, what kind of courses you're teaching before, and who your advisor is, because from a thesis advisor, I roughly could pick up the field of practice. Okay, thank you.